Thank you, Benjamin. Good afternoon for everybody. Thank you for the presence. I will turn it on so I can realize the time that's spent to the end of the conference. And now I will present the project that is the theme of my sabbatical. I'm here since August for a one-year sabbatical, just doing research in that theme. So it's the application or adaptation or maybe a suggestion of a modification of neural networks methods to cognitive diagnostic models or assessments. These are my emails from Brazil and from the University of Iowa, because I'm working in collaboration with Sueli Oliveira, which is a professor of the computer science department at the University of Iowa, and Jeffrey, and another Jeffrey, two Jeffreys, Jeffrey Converse and Jeffrey Hajeski, which are her PhD students, And also I'm working in that team in collaboration to ACT with Benjamin and Previn. So I have an email here too, and in Brazil. The content of the talk of today, I can divide in 4 parts. The first part, I will talk about the artificial neural network method, the traditional one, the first proposed in the middle of 20th century. The second part, I will talk about the bibliography research that I made in order to propose the methodology that I'm proposing now. I made some research in the internet looking for articles that applied neural networks to cognitive assessments. Then I will talk about, in the third part, I will talk about the proposed method, which is the neural networks applied to cognitive assessments, and why I chose these 2 themes. Well, neural networks I chose because with the fashion of data science, I began to study machine learning methods. So I began to study random forest, lasso regression, support vector machines, neural networks, and that stuff. And I realized that neural networks are methods very related to logistic regression, which are related to item response theory models, which is related to my research area. And I like it very much. So I think it's a good method among all of the methods that we have in machine learning. I think it's a good method. It works, at least now. In the middle of the last century, it didn't work very well, but now with deep learning development, these methods works better. And it's close related with the models that we use in psychometrics. So that's the reason I chose neural networks. And cognitive diagnostic assessment, I chose because I think it's a situation that is more related to the classroom. And I'm a researcher, but I'm also a professor. So I have students, I give classes, and I would like to use the methods that I research in the classroom. And formative assessment is better than summative assessment in a low scale sample. So I decided to work with cognitive assessment, cognitive models instead of item response theory models. And the fourth part, the last part of my presentation, I will bring some ideas that I have to study the method that I will propose, and some ideas that I will study during my stay here with all of my collaborators. But I have more ideas than the ones that I am able to work in this year here. So I will present their ideas, maybe to have some collaboration after I come back to Brazil, okay? So beginning with my first part, the artificial neural networks, the traditional one, what we have here. We have layers. The first layer is called input layer, where we insert the data that we observe, the exploratory variables that we have in our data set that we observed, and I'm using the index I with P nodes in this input layer. One represents each observed explored variable, okay, independent variable. We have one or more hidden layers with the number of nodes that we can define depending on the occasion, and one output layer with the labels that we know, the response variable or response variables that we have in the data set. I'm representing that output layer with the index O with Q possible response variables. And what we have connecting these layers, we have the connection between two consecutive layers. And these nodes in the first layer are connected to all the nodes of the second layer that I'm representing, just one hidden layer here. And we have a function connecting these nodes. And this function, we have weights or parameters, as we say in statistics, relating each input variable to our node, the first node in the hidden layer. And also we have a bias. The computer scientists call that bias, which is our intercept of the function, relating each node of the input layer to each node of the hidden layer. And we have the same model, the same structure, relating the hidden layer to the output layer with different weights or different parameters relating each node from the hidden layer to the output layer. And then we have the output, which is the label or the response variable observed. So this is the structure of a simple neural network method. And we can use an activation function or a function that relates these nodes between consecutive layers. Here we have the weights, here we have the bias or the parameters and the intercept relating the input data to our first node of the first hidden layer, or the node H of the hidden layer. And we have a function relating that, which can be a logistic function, as we have in logistic regression, or it can be another function. There are other options of functions for that relation, but the logistic function is one very used. And then we have the Z, which will be the output or the exit of this node of the hidden layer. And this Z is again used to relate the hidden layer to the output layer in an analogous way, okay, using the same function that I choose as logistic function and relating to the output data. So we can write this in matrix notation to become better. And we have other options of activation functions, for instance, the hyperbolic tangent, that it will be important because it's related to our work. And we define some loss function that we have also many options, for instance, the mean square error or the cross entropy or others, in order to obtain these weights, the estimates of these weights W and W star, and also the intercepts, the B, or the bias, as the computer scientists call. And we have many options for this loss function. I will talk about one in special, the cross entropy function, which is adequate when we have binary classification, when we have binary outputs. And it's defined like this equation. So it's an expectation. And algebraically, we can show that this equation is exactly this one, which is very similar to the likelihood function of a logistic regression model. So we have, this is the core of the likelihood function, the log of the likelihood actually. Y is the observed answers, the observed response variables. Y hat is the predicted, so the prediction is related to the input or the explored variables. And this is exactly the log likelihood multiplied by some constant, negative constant. Okay, so minimize this entropy function, this loss function, is exactly the same of maximize the log likelihood function. So there is a relation if we have a log logistic model written as a neural network, and the things that are very close to each other, the neural networks and the logistic function. Okay? And the logistic function, let me come back here, is a special case of a neural network. It's a special case when we have just one hidden layer with one node, and the function that we choose relating the input layer to the hidden layer is identity function, and the linking function or the activation function linking the one node here that we have in the hidden layer to the one node that we have in the output layer. We have also just one node in the output layer, is the logistic function. So the network written as this special case is a logistic model. Okay? So there is an analogy or a similarity between neural networks and logistic function, but neural networks methods are more complex because we can input more things than the logistic function or the logistic model. But the algorithms that the computer scientists use in order to minimize that function is usually the gradient descendant algorithm, which is also related to the algorithm that we use to maximize the log likelihood function, which is can be the Newton-Raphson algorithm. They are related. They are not exactly the same, but they are related to each other. Okay, so there is a relation among neural networks and logistic model. The second part of the talk is to bring the articles that are published in the literature that they use the neural networks to cognitive diagnostic methods, models, or assessments. And in general, these articles apply neural network methods to cognitive diagnostic assessments, but without proposing any modification of neural network methods. And the biggest difficulty is that neural network is a supervised method, and cognitive assessments is not supervised. We don't have the labels, we don't know the classifications of the students. So until recently, neural networks methods were not so fashion applied to assessment, cognitive assessments. Until more or less 2 years ago, I will cite here deeply 4 works that I found in literature that apply neural networks to cognitive assessments in some way that is not just an application. This first one, that is a work published in 2007, is just an application, but it's an application very important to the others' work that I will cite here. Mark Girl, I don't know how to pronounce this name correctly, but Mark Girl is a professor at the University of Alberta at the Department of Educational Psychology. And coincidentally, Benjamin sent me a message saying that He is the header of a company that in some way made some deal with ACT recently in order to acquire this automated item generation technology. But in this article of 2007, he proposed an attribute hierarchical method, which is based on the rule space model, and he used the neural network to confirm that proposition, that model that he's proposing. But the traditional artificial neural network, and how he leads with the classification, the output classification that actually we don't have. He leads generating inputs and outputs, actually generating outputs that are theoretically supposed to the students. For instance, if I have a neural network here, so the input layer, we have the answers to the items that we observe. We have the leader layer, and we have the output layer with the information of the skill. We define if the student master or don't master each skill that are involved in the assessment. And if you know the Q metrics, and he is proposing a hierarchical metrics where we take in account the order of the learning. For instance, a student first learn how to add, then learn how to subtract, then how to multiply. There is a natural order. There is an hierarchy in that. So using that hierarchy to define the Q metrics, and using these Q metrics to define how are the skills of the students that answers all the items correctly. For instance, all the items corrected, this student will have all the skills mastered. If the student answered all the items incorrectly, this student will not master all the skills. And among these two extremes, we can define theoretically how is the master and non-master pattern for a student that answer the items in certain way. So he used this, I will call that theoretical data, to apply the neural network model, and then he has a model trained or estimated to apply to new students. So this model trained with theoretical data, he can input new item responses and predict the skills of these new students. Okay. The second work, also from Mark Girl and other two colleagues, they used two methods of machine learning applied to cognitive diagnostic assessment. One of them, also, the neural networks applied to theoretical data, just the article that I presented before. And the second is an unsupervised method called SelfOrganizing Method, which is basically a clustering method. So the problem here, it's not a problem, but the difficulty here is after you cluster the data, the individuals, based on some similarity index, we have to interpret that cluster. And we close the door. Okay. We have to interpret that cluster. And interpret that cluster is not so easy. Okay. Then the two co-authors of the last article that I described here, and another colleague from the University of Alberta, Kutumisu, in 2017, they proposed a method really interesting. It's a non-supervised neural network, and the novel here is the unsupervised. I'm in front of you, I'm sorry. Which is the structure of the neural network that we know. But the difference is what to do with these outputs. The outputs in this method, which is called autoencoders, is exactly equal to the inputs. So we have the answers of the items here as the input layer. Then we have the hidden layers, and the output are exactly equals to the answers of the items, exactly equals as our inputs. And what is the idea? The idea is to have a hidden layer or more than one hidden layer with less nodes than the input layer. So we are shrinking the data, okay, in some way, using the activation function of the neural networks that we talked about. And the number, let's take this last hidden layer here. The number of nodes of these last hidden layers is equal to the number of skills that we have, or attributes that we have in the Q matrix. So we are shrinking the item responses to the number of nodes that represent our skills. So each node of this hidden layer will represent one skill that we are assessing. And then we will construct again, based on that skills, we will construct again our responses. So how can we shrink the data in nodes that represent one of each skill, and in order to reconstruct the data, the better we can. Okay, that's the autoencoder, and this is the normal autoencoder or the vanilla autoencoder. But the modification that they proposed is in the connection between the last hidden layer and the output layer. The connections here, the nodes of this hidden layer, are not connected to all the nodes of the output layers. They are only connected to the nodes that represent the items which assess that content. Okay, so here the connections are defined using the Q matrix. Okay, is it clear? Okay. Another modification of the autoencoders that they have here is that these hidden layers can be 1 or 2 or 3 or 4. Here they define it as 2. And this is also a modification of the vanilla autoencoder, because in the vanilla autoencoder we have an odd number of hidden layers, because the middle layer is like a mirror. So we shrink the data until the middle layer, which represents our skills, and then we recover the data like a mirror with the same number of hidden layers in the second part of the method. And here they are not using that. They are using just 2 hidden layers and define these connections using the Q matrix. So this is not another modification that they propose here. He could, I thought when I was reading the article, I thought, why they don't use just 1 hidden layer? It's simple, why 2? But then studying, I realized that if we use just 1 hidden layer, this method will be related to principal component analysis. It will not result in the same loadings of principal component analysis, but in a modification, a projection of that loading. So these methods, principal component analysis and these autoencoders with 1 hidden layer are related. So they proposed using 2 hidden layers. And they simulated data. How I forgot to see how time do you have? Okay. So they simulated data. I don't remember if based on a DINA model, maybe yes, and compared the results of this data with the results of the DINA model estimation. And they realized that the skill estimation accuracy was similar, but the recovery, can I take this out? The recovery?
It's stuck down there.
No? Okay. But the recovery of the skill properties, maybe I think it's the, well, I don't know. I think it's about the hierarchy. So there is a hierarchy. Remember that they are from the University of Alberta, and at the University of Alberta, they suppose that there is a hierarchical in the skill. So this recovery of this hierarchical structure was better recovered using the neural networks model than the DINA model. And recently, this work was present in the Educational Data Mining Conference of this year. Shu is a professor of the University of Georgia, and he proposed also use an autoencoder, but with a modification compared to the work from the University of Alberta. When we have, here we have 3 hidden layers. Here the middle hidden layer is related to the skills. I'm in front of you again. I will be in front of Praveen now, or nobody. So the middle hidden layer is related to our skills. And in the test, remember that the input and the output are the answers of the items. So in the test, we have what they call simple items. What are simple items? Are items that are related just to one content, one skill. And complex items, items that are related to one or more skills. And the skills that are assessed in the simple items, they know. So they know the Q metrics for that items. And the skills that are assessed in these complex items, we don't know. So we don't need to know these Q metrics for that items, for those items. So for the items that we don't know which skills they measure, we link to the nodes of this last hidden layer here. And these nodes are connected to all the nodes that represent our skills. And these simple items are linked directly, not with this middle layer here, but they are linked directly to the skill, to the node that represent the skills that we know that they measure, okay? So with this model, he also made simulations varying test length, the number of simple items, and the discrimination power of the items. So I don't know if you are aware of is the discrimination power of an item in a diagnostic assessment. Yeah, I wasn't too, and I found that it's more or less like the discrimination power in a classical test theory. So we suppose that an individual has some skills. So based on that skill pattern, we can calculate the probability of an item being answered correctly based on that skill. So if we suppose that the skills are mastered, we calculate the probability of the answer, the correct answer of an item based on a very good student. And calculated the same probability, the probability of correct answer of a student that doesn't master the skills, and compare the difference. We calculate the difference of these two probabilities. If this difference is big, so the item is good, has a good discrimination. That is the discrimination power that he's talking about. So he compared that and realized that the accuracy attribute estimation is among 70 and 90%, which is not bad. Okay. So based on that 4 works, I think neural networks autoencoders, which is an unsupervised method, could be very interesting theme of study. And thinking on autoencoders, where we have the exit of the node of the middle hidden layers of an autoencoder is the probability of a student master that skill that the node represents. And that probability is a number. It's calculated in the autoencoder as a number. But there is an extension of the autoencoder method called variational autoencoder, where that number is stochastic. So we have the probability of a student master the skill, but we have a probability distribution to that value. And this is the method, this already exists, is the variational autoencoder. It was proposed in 2014. It's an unsupervised method as the autoencoder. It's a deep generative neural network, because with that, can I say a posterior distribution of the skills? With that posterior distribution of the skill, given the inputs, the item response, we can generate data. We have the distribution, we can create data. And the computer scientists use that model to create data because the inputs are images. And they create parts of the images to improve the resultant images. So they call that generative neural network. I will first show the structure of the variational autoencoders. So we have something very similar to the autoencoders. We have the inputs, which are the answers of our items. We have the outputs, which are also the answers of our items. And we have hidden layers here. So we first shrink the data to a middle hidden layer. But this middle hidden layer, which are latent variables, we will associate to them a probability distribution. That's the reason I insert this graphical here. They use what kind of distribution? The normal distribution is the traditional distribution that they use in the variational autoencoder. And then to connect these first nodes of the first layer to this hidden layer here, which will represent our skills, the number of nodes also is the number of skills that we have. We shrink the data in a part that we call encoder part or recognition model. And then based on that distribution, posterior distribution for the latent traits, we regenerate the data again. And this part of the analysis is the decoder or generative model. Generative because we can generate data from the distribution that we reached. So how can we do that? We find these weights that are connecting the layers. Also, again, we have a loss function. The loss function will depend on two vectors. The first vector is representing, and I will come back here. So what do you want? You want a distribution for theta, which are our latent variables, based or given the response of the items, given our X inputs. So using the conditional formula, probability formula, we can rewritten that as the probability of our answers given the latent trait. I'm restricting that to our situation where X is discrete, but of course it can be extended for X continuous. Okay, just taking some corrections to the notation. So the probability of X given theta, our latent trait, and some prior distribution for theta divided by the probability of X. And the problem here is in the denominator. So we have to calculate this probability with some integral. If we have theta unidimensional, it's easy. We can define nodes for theta and calculate using some numerical approximation for this integral. But if we have theta multidimensional, this calculus will begin more complicated. So for high dimension of theta, this will be complicated. So what is the solution that they have using variational autoencoder? Is to approach this posterior function for theta by another function simpler than f, but able to reconstruct the data well. So here we have this function, this posterior function that we want to approximate the original one, the real one. And another function to recover the original data based on the latent trait that we estimate. And these two functions, key, conditional function, Q and P, are parameterized by some vector that I'm representing by alpha and beta. So the loss function is depending on alpha and beta vectors, and it's we assume independence among individuals, of course, and well, I don't know, of course, but we are assuming independence among individuals, and we can write this loss function as two parts. We can divide into parts. One related to the probability of observed the data that we observe, and another related to the distance or the divergence among the function, the real function of theta given x that we don't know, and the function that we are trying to approximate f. Okay, and this function, the form of this function, we choose as Gaussian. Okay. Algebraically, we can rewrite this expression like this one here. So it will be a sum of some function of our probability of the data given the theta, that is Bernoulli in our case, and the Kullback-Leibler divergence among the function that we are supposing normal to theta given the data, and a prior function, a prior distribution function that we also assume for the latent trait. And we also assume that as Gaussian, as a standard normal Gaussian, as we do in item response theory models. Okay? What time is it? Já passou? Oh, no? Oh, how long do I have?
7 minutes.
7 minutes. Okay. Oh, it's in regressive context. Okay. So this is the method that already exists, the variational autoencoder that already exists. And what I'm proposing to do to modify in that method to apply in cognitive assessment or in assessment in a general manner, because I have latent traits that are supposing to be normal. Okay, so I remember the item response theory models. I'm proposing the modification of these connections between the last hidden layer and the output layer using the Q metrics to define them. So I will have the same, but this decoder part will be defined by the Q matrix. I will only connect this node, which represents one skill, to the items that assess this skill, this content. And here, in the middle, where we have the latent variable distribution estimated, I would like to estimate the probability of the student which give some responses to the items. I would like to estimate the probability of that student master that skill. So I have a probability for that probability. I have a probability distribution for that. So I have to estimate that in any way. But with the probability, I can estimate using the mean or the maximum or well, no, thinking on Bayesian inference, we can choose, and I choose for our simulations, I choose the mean. Okay, I take the mean of these distributions representing the probability of a student master some skill, any skill. And I simulate some data and applied the variational autoencoder, the traditional one, the vanilla variational without my modifications before. And these are the results that I have now. So I simulate data using 5,000 subjects, 5 skills, 30 items. I simulated based on the DINA model, but we can change that if we decide it's better. And I used the Psychometrics that was already used by other author, by De La Torre, in this article of 2009. I assume guessing and sleeping parameters all equals to 2.2. So we have five skills. So we have 2 to the power of 5 possible response patterns. This I doesn't here. All with the same probability to occur. And I analyze that data with Jeff in Python. We could use R. There are some packages that exist to analyze variational autoencoder in R. These are 2, Keras and NN2 for the autoencoder, and Keras for the variational autoencoder. But it's not so easy to program and to insert the data in Keras. So I prefer to use Python with the help of Jeff. And there are something interesting using Python and trying to understand the algorithm that they use to minimize the loss function. They define 2 things named batch and epochs. Do you know, are you aware of that batches and epochs? I was not as well. But instead to obtain the estimates of the parameters using all the data, they divide the data in subsets. And the number of subjects in each subset is what they define as batch. So instead of train the model with all the 5,000 subjects that I generate, they divide it in subsets with 50 subjects in each subset. And of course, they use all the subsets to obtain the method, but in some way that I still don't know exactly how it is. And the epochs, I don't remember exactly what it is, the epochs, but it's also a manner with these 2 numbers to train the model without using all the subjects at the same time. So it will make the algorithm be faster. And here, I think what's interesting in that graph is the time to train and to obtain the results. They took 3 seconds. So one of the problem of the neural networks, that everybody say, oh, to obtain the results, it gets too much time. The running time is too high. But here, it's 3 seconds. It's really fast. And we decided that the loss function is becoming lower if we increase the epoch. But after the epoch 10, we don't gain much in that loss function. So we decided to fix the epoch in 10. I still don't know what it means, but it's a better way to obtain the results and to obtain faster the results than what we are used to do with all the students at the same time. Oh, are you okay? What happened? Okay. Well, as I don't use the Q-metrics to decide which node of the last hidden layer will be connected to the nodes of the output layer, these nodes of the hidden layer doesn't represent exactly the, is that mine? Oh, my time is up, but it's ending. So the skills that I generate in the middle hidden layer doesn't represent the skills that are in the Q metrics. So it's a mess because I don't use the information that I have in the Q metrics to define which links, which connections I will have between the last hidden layer and the output. So I didn't use the hidden layer results to analyze yet my results here in the simulation. What did I use was the predict answers to the items that I obtained in the model with the original answers to the items to see if the students answer correctly the first item, my model will predict it as correct or incorrect. So I calculate the accuracy for each student and calculate the mean of that accuracy, and it was 75%. And this is the histogram of this accuracy among all the 5,000 students. It's not bad, but of course, we can improve. Modifying the model in the manner that I propose, I really believe that we will improve that a lot. Another thing that we can use to improve that is to study the number of hidden layers that we have and the activation functions that we will use. I use here the hyperbolic function, the hyperbolic tangent. With the logistic function, the results were worse, but with the hyperbolic, we have that. But we didn't explore the other alternatives that already exist in the method. So I really believe that we will improve. I expect a lot that result. And this is an example of the accuracy for one student. So the model predict correctly 70% of the item answers for that student. The blue one is the prediction of the model. The orange one is the real answer of the student. So we have this, the model predict correctly and this incorrectly and this incorrectly and so on. So these preliminary results show me that I can believe in that method. I'm really hopeful with that. So what I would like to study that now, we would like to develop the variational encoder to implement the variational encoder in TensorFlow, incorporating the Q metrics to the connection of the last layer. Simulate data and compare with the other models that we have in order to see if it's better or as good as the DINA model, for instance. We can vary the dependencies among the skills because the method supposes that the skills are independent, but we can input a covariance matrix and calculate all the weights supposing correlation among the skills. I would like to understand the structure of the hidden layer to understand our skills and the relation among them. We could investigate the discriminating power of the test item using the decoder part, because once we have the latent trait, we can fix that latent trait and generate the answers based on that latent trait. So I can fix the latent trait in a good student that master all the latent traits and generate the answers and the probability of that answers, as well as the probability of the answers for a bad student that doesn't master the skills, and compare that probabilities, calculating the subtracting one of them and calculate the discrimination part, the discrimination power of each item. And maybe when I come back, I don't know if I have time to do all of that here, but I would like to compare this variation autoencoder method with the models or some of the models that we have in item response theory and in cognitive diagnostic models, because I think or I believe that some particular case of a variation autoencoder is related to the models that we have in psychometrics. I would like to modify the distribution assumed for the latent traits. So we can, instead of assume Gaussian distribution, we can assume other distribution, other discrete distribution, for instance, thinking on a cognitive diagnostic model. There is some work published very recently in 2017 proposing another distribution that's not Gaussian. In the literature, the name, the article is proposed is stick breaking variational autoencoder. And I also would like to test if I have observed data more beyond the correct or incorrect answers for the items, because I can have other data, for instance, the time to response of if the student ask for a tip for that answer or not. So we can collect other data than the answer to the item. And it's easy to input the data in a neural network model. And maybe we can use convolutional variational encoder, where the convolutional that already exists, the convolutional neural networks, we connect just a set of nodes to the node of, or to the nodes of the next layer. So there is a method that already is proposed in the literature that we can use to analyze that kind of data. And I also would like to study that methodology applied to model that assess misconcepts and not skills. So that's my plan for the next, I don't know, years. I don't know. And these are the references, some of them. And that's it.